So welcome everyone to the 8th session of. So now, no more time waste, I'd like to request Abhishek sir to introduce Mr. Subhro Sinharoy with us. Sir, please, over to you.
Thank you, Madhumita. It's an absolute pleasure today as we move to the 8th and the penultimate webinar talk, which started on Monday. And it's my pleasure to introduce Subhro, who is not only an astute geophysicist, a very competent geophysicist who is in a principal role currently working for Equinor in Bergen, Norway, but is also a very close friend who I can turn to at any point of time, and I know he would do his best. And this is also a testament that with a very short notice, he was away the most of last week, but he could still come up with what you're about to hear in the next hour or so. So just to put everything in context, if you go back to the first setting the scene story, we now have a prospect where we have drilled multiple wells, and we have appraised, we've got enough data through well log interpretation, VSP, that we have run an inversion studies. We have now, with the aid of seismic, become confident to actually go and make a field development plan based on which we have started production. So Subhro takes today's topic, which is titled Digital Oilfield Enablers, Key Enablers, but he will soon expand upon various aspects of it. This is essentially to fulfill two roles. One would be around the maintenance of reservoir performance, so that geophysics playing a big role in making sure that the production profile that we promise to the business we deliver. And the other key aspect is when that production starts to subside, what kind of enhanced schemes could we put in place to keep that up? So just like you all, I am looking forward to hear this engrossing talk which is about to take place. So over to you, Subhro.
Thanks for the introduction, and thanks to all of you for hearing. It's a privilege for me to see so many listeners and my teacher, Dr. Shaw. It's really a privilege for me. Let me now share my screen. Give me a second. Yes. Yes. Can you all see the screen now?
Yes, sir. Absolutely.
Yeah, thank you. Thank you so much. So today's topic with regard to the digital oil field, as introduced, we'll talk about some of the key enablers out over here, and I'll touch upon one of the topic which I have worked quite a bit for a while. But before that, we'll take you through some of the broad objectives of digital oil field, and how do you think that we approach to achieve it? And then before going into the details of the project on permanent reservoir monitoring, we'll give a bit of a teaser on 4D seismic. I believe all of you are quite aware of it. What is 4D seismic? But I will still give a very short introduction as to what 4D seismic is and what do you do with it and what's the purpose. And then we'll summarize. If you have questions, do put it on the chat box. If the same question is being, if somebody else have in your mind, put a like on it. So we understand that, okay, you have got a repeated question and we'll try to prioritize to answer that. Of course, we'll take all of the questions in the Q&A session as well. But it's good to keep it documented as well so that we have it for reference later on. When it comes to the broad objectives of a digital oil field, why are we talking about digitalization today? I mean, if we look back 10, 15 years back or 20 years back, we have been looking into digitalization of well log data, scanning of well log paper sections and digitalizing them. Things have moved on from then, and now we are trying to digitalize essentially anything and everything. So that is something that we have taken up, and we have seen the benefits of it. And today we are looking at digitalizing oil fields, meaning that we want to have the information, as much as information possible in one go, and that we achieve it by having all of these relevant data in formats which we can access and utilize and turn them into information. In today's world, where we are suffering, or the industry is suffering from different kind of challenges, be it climate change, be it oil prices, etc., and COVID-19 on top of it, where the sustenance of the industry is being questioned. Under these circumstances, where we need to build upon in the industry is building efficiency and collaboration. Collaboration is a term which is not something new to us, nor efficiency, but there's a broad impetus right now that we need to focus even a bit more on these two terms. These are the founding blocks out over here. When it comes to the collaboration, we have talked about, in geoscience domain, we have talked about multidisciplinary data analysis, bring in all kinds of data. So essentially, we understand the broad idea of collaboration. But the thing is that we need to collaborate beyond data. We need to collaborate two people, two organizations, and we need to work together to make it happen. That's the whole purpose out over here. On top of this, we have got what we need to generate in terms of resources is high value. So all of these resources, it has to be high value. And when it comes to high value, do not misunderstand that high value does not mean that we need to find reservoirs which are really huge, with huge potential, multi-million barrels or few billion barrel reservoirs. The point is not that. It has to be, when it comes to the production, we have to be quite efficient in terms of the cost. That is, the cost of production must be quite low so that we are able to run the business efficiently. And that's the core of it when it comes to the high value. And whatever operationally we do, it has to be safe and it has to be low carbon. That's how our industry, our experiences. Our experiences, this is a time where we are challenging our experiences, that our experience should be more data-driven than just few projects, because there are aspects in which we have not been able to use all the kinds of data sets that we have or make full use of the data. So that is something that we're looking forward with all of these technologies to use the data, all of the data sets that we have to the fullest capacity, so that we are able to utilize the entire data sets to turn that into information and use it for decision making. And third and most important is collaborative culture. That is something that we see in the organization as a must need. There is no time for thinking about benches. We are small blocks out over here with geophysicists, geologists, reservoir engineers, production engineers, drilling engineering, economics, and so on and so forth. This is a time where we need to sit together and look into our data sets, analyze them, and come out with a decision. We'll talk about the enabler of permanent reservoir monitoring. Before that, we'll go on a bit of a teaser on 4D seismic. I believe that most of you are aware of about the topic of 4D seismic. If not, ask your teachers. They should be able to help you with it, or ask your friends who knows about it, or Google it. You've got a very good resource nowadays. When it comes to the 4D seismic, we'll talk about, essentially 4D seismic is about monitoring. So if we look at about the term monitoring, when did it evolve? I started looking into the term reservoir monitoring into ARTOC. From 1970s onward, if I look at it, it essentially came in the 1990s when people started talking about reservoir monitoring, the publications on it. Late 90s, in the year 1999, 2000 onwards, you see a boom in this reservoir monitoring, or all of these monitoring words. And then onwards, it has become an exponential boom. Of course, there has been dependence on oil price. I put the oil price out over here, how the oil price has been with regard to the dollars with different years. So the publications tend to rise quite a bit when the oil price is high, and actually the next year when the oil price is low, it's highest, and the next year when the oil price goes up, it feels the sensation of the low oil price and it reduces. So this is kind of the structure. But the main motto out over here, as we see here, 4D seismic, reservoir monitoring, essentially all of these things picking up since the late 1990s. And from the year 2000 onwards, you see a peak in it. So it's fairly a recent topic. I'd say 20 years is very, very recent. And when it comes to the geoscience domain, we are kind of very slow creatures. And when it comes to the overburden monitoring, at least there has been publications even earlier to that. But there is, of course, when it comes to overburden monitoring, we see that there are more number of publications coming of late. People are getting aware of it. And I'll introduce about overburden monitoring a bit later on. Now, 4D seismic, what is it? What it does? So I've got two pictures out over here. At time X, you've got a subsurface cross-section where you've got oil at the top and water down over here. At time Y, later on, what has happened? You have produced, so you've got water flushed into this area, and the oil, you have got a cap with oil out over here. So if you make a difference between these two time periods, this is what you get. You get the water flush zone, where you have essentially replaced this part, which had oil earlier, with water. So why did this? So what we are interested in is, the key word is, we are looking for a change in two different times. That's what we are looking in 4D seismic. And what is this change due to? Only two aspects. One is fluid saturation changes, whether it's due to gas, oil, and water, or it's changes in pressure. That's in a simplified tone. These are the two things that matters. And then, but physically, what is happening between these two time steps? In this particular example, what you're seeing out over here is that you are seeing that the acoustic wave, which is traveling through this particular zone during this particular time period, and this time period is varying. And essentially, the time taken, the velocity is changing between oil and water. And there are some changes in density as well because of the fluid type, though it is very minimal contribution, but still. And there could be associated pressure changes. In some fields, it could be just saturation changes. Hardly you see any pressure changes. In many other fields, it could be just pressure changes, very little of saturation changes. That is kind of magnified on seismic, which I'll come a bit later on. And in other fields, it could be a combination of both. But beyond the reservoir, what happens in the overburden, which is above the reservoir? And I did not introduce out over here the underburden, which tends to happen down below here. Well, there could be compaction or extension in the overburden and the underburden due to production or injection within the reservoir. I'll come back to this topic a bit later on. Then again, seismically, what happens? What is the manifestation on seismic as to the velocity changes that is happening, which is leading to the changes in the travel time? So what you're going to see here is that due to the change in the saturation, or the pressure changes, you're going to see changes in amplitude. In some cases, you're going to see very beautiful amplitude changes. Some cases, the amplitude changes could be very minimal. But definitely, in general, what responds is there should be a change in the travel time, and due to the change in the velocity within the flush zone. So this is kind of a key thing that we tend to happen to see. Amplitude changes in some fields is very, very pronounced. You see it very well. Some fields you might not see it that much. And where it helps is data quality. And I'll come back to that a bit later on again. Now, to explain further on this saturation change, what is happening out over here for when you're talking about a reservoir, where I'm just going ahead for a change of acoustic impedance, which is lower in the reservoir than in the surrounding matrix in which it is encased in, meaning the overburden and underburden has higher impedance compared to the reservoir, which is lower impedance. The reason why I choose it, then the convention becomes easier to explain, and then you can understand what's going to happen for the other way around when it's higher impedance reservoir. For this particular case that we have described, I'll just continue with it. In this, we have what we are having. We are having water is replacing the oil here. So what is happening in this particular case, we are getting velocity and density changes. And what is happening with water is we are getting a velocity and density increase during this particular time period for this particular zone. So when it comes to the rock physics terms, essentially we call it that it's getting hard with increase of velocity and density. So seismically, what's the imprint? Amplitude usually reduces. And when it comes to the time shift, there is an upward time shift because the velocity of the water is faster. In case gas replaces oil, for this particular case where gas is replacing oil, it's going to go the other way around. Velocity and density is going to decrease. So it's going to get even softer. And the amplitude should be increasing. And the downward time shift is going to happen. So it's going to take more time for that particular zone for the wavefront to travel. So velocity in water is faster. It's important to remember when it comes to the gas, it's a typo here. So velocity is going to be slower when it's moving through the gas. Now, what happens with the pressure change? For a reservoir, for the same kind of reservoir, we have got a lower acoustic impedance within the reservoir compared to the overburden and the underburden. If you start depleting a reservoir, meaning that you are producing out, what's going to happen? The pressure is going to reduce. And when the pressure is going to reduce, your grains are coming more in contact with each other. And as a result, the velocity is bound to increase. So when the velocity is increasing, in this particular case for a depletion, what's going to happen to the seismic amplitude? It essentially reduces. It's the same principle that you have seen for water replacing oil. So seismic amplitude is going to reduce, your time shifts are, it's going to upward movement of the time shift in the monitor. That's what you're going to see. So essentially, if you see here, from the initial, if you have an acoustic impedance increase, if you have a depletion, you're going to get an acoustic impedance increase. If your pressure is increasing because you're injecting water, for example, your acoustic impedance is decreasing. And as a result, when you look at the relative change in the VP and acoustic impedance versus effective stress out over here, this is kind of the plot that you are going to see. So I'll show more examples on all of this, but this is essentially the basic behind it. Now, this is a pure case of pressure change. Now, think about a case where saturation, in fields where saturation and pressure both work together in certain degrees, then it becomes much more complicated to understand. And that's kind of the dilemma and the fun part to work with it. When it comes to the mechanism of changes of within the reservoir and the overburden underburden, this is essentially what happens within the reservoir. If you are producing, it creates depletion and it gets compacted. As a result, this part kind of shifts down over here. And your overburden keeps extending. And it's many a times it's manifested with the seafloor sinking as well. We have seen many fields where there is a subsidence on the seafloor. Ecofisk, I cannot remember the values, but it's essentially a chalk reservoir. So it has compacted quite a lot, and there is a huge amount of subsidence. Entire platform has sunk for quite a few meters. So in this particular case, if you look at the time shift is increasing with depth in the overburden because there's a depletion within the reservoir. And then in the underburden, once again, it goes up. And that is because of the velocity changes. So what happens in this case, you've got increased velocity in your reservoir, leading to a decrease in velocity in the top part and below part out over here in the overburden and underburden. When it comes, this is kind of the schematic or the physical principle in which it works. If we look at pure examples in the field, so we are looking at one of the fields out over here. It's a high HPHT field, shear water. There is a 60 megapascal reservoir depletion between 2004 to 2001. So what we have seen out over here is a depletion of around 6 milliseconds, or a reduction in the time shift by 6 milliseconds in the overburden and the underburden due to depletion in the field. In the other way around, when we have injected in this particular field, there has been a gas injection. We see opposite effect in the time shift out over here. That what we have done here, we have seen a slowdown out over here due to the gas injection. We have got a pressure build up here, and naturally we have seen a speed up in the overburden due to compression out over there. So this part, it can compact or extend depending on what we do in this part in the reservoir. Then we move on to what can we observe on 4D seismic and the value propositions of it. When it comes to the reservoir monitoring part, what are we observing here, or what do we try to observe? We try to observe the fluid fronts, how it is moving, whether it's gas movement or water movement, how are they moving? Because that has got absolute importance for us in how we produce the field and what is going to be our strategy in terms of how we produce the field over time. And what we try to do, we map the changes in the saturation and the pressure. We try to understand if there are bypass compartments, like there might be compartmentalization within the field due to the faults. Some faults are completely sealing, making it kind of areas where we are unable to produce from. Or there could be some blocks where we are exclusively producing from. We done information about whether all of these faults are sealing or non-sealing. It's many a times driven by geological understanding and production data with regard to the faults. Many a times we go wrong with all of this information we think that we know. And that's where 4D seismic comes and helps us in understanding whether the fault blocks are really sitting down in silos or they're in communication. So that's kind of very, very important thing that we try to understand. We also try to monitor the fracturing and the stimulation operations, meaning that we have got perforated sections along the wells through which we are producing the hydrocarbons. Many a times there could be sand production. There could be other issues due to which all of these, there are different kind of completions that we use. These completion screens, they can get damaged and things like that, and we can lack productivity. So there are different kind of fracturing mechanisms which are being used later on, from acidization to bullheading to different kind of stimulation techniques, where essentially the whole idea is to create a pathway for hydrocarbon to flow into these screens. So that is something that 4D seismic tells us, and I'll show you examples of it, that which part of your screen is really producing and which is not. Then comes the quantitative aspect of production tracking. So normally, how a well is producing, we normally try to understand it from production logging. That is, when a well is producing, we try to run a production logging test. And we try to, what we do is we measure the production rates there at different time points to understand what is the flow potential. In many fields, we are unable to perform production logging due to different reasons. Operational reasons, somewhere we are unable to do it, somewhere we are unable to prioritize this. And also it's important to remember that in many cases, when we try to do production logging, it's along a borehole. So it's just a 1D information that you're getting. In particular seismic cases, it can be really quantitative. Your seismic amplitude can give as good an information as your production logging test does. And I'll show you some examples of it. When it comes to when you move from the reservoir to the overburden, you're trying to look for stretching and squeezing of the overburden and the side burden and the underburden to understand how your overburden is behaving. That has got important, that is absolutely important when it comes to operations, that you should be, for HSE reasons, for safety reasons. It's important for formation integrity, from where you are producing, or you might be injecting in the overburden. In many fields, what we do in the North Sea, whatever we produce from the reservoir, there are cuttings and injections, cuttings that we have gotten, or the water that we are producing out from the reservoir, we inject in the overburden in certain formations which has got sand in it. And this is something that we are really careful about. We try to inject into sands. We try to monitor them where it is possible to see that we are not breaching it. And that is absolutely important. Then what can we use all of these observations for? We are observing it, observing whatever I told you in this particular slide is what we are observing. Then what are we going to use it for? We are going to use it to plan in infill wells, in matured reservoirs where we have been producing for quite some years. We are trying to understand which are where is the oil left, and we have to put in infill wells there. And that has to be done with perfection. And that is something that we use 4D data often for. We have to understand the sweep potential, which is remaining, so that we can sweep out the oil very effectively. We need to maintain the production with injection management. So what we try to, when we decide that we need to inject oil and gas or water into the reservoir, it can be different sources of information that we get, either from productions. We get information as to, okay, in particular areas, we might have suddenly that we have got an increase in pressure or decrease in pressure, or we have got fluid fronts coming in all of a sudden, which we didn't understand earlier. And this is something that we try to model and understand, but there are limitations in it. Where 4D seismic comes in and helps us out over here is that surprises, meaning that those information that comes as a surprise to you is something most valuable when it comes to operations of the field. And this comes into the production and injection management. In some places, we feel that we are producing effectively. We get a number, but of course, where you are getting the production from within that particular well, is it from the toe part or is it from the heel part of the well? That is very important for us to know. Secondly, do you need a water injection or a gas injection in a particular area? Many a times we think we know the answer, and most of the times we are wrong. And that's where 4D seismic helps us to understand what is happening actually in the reservoir, and we take decisions driven by the data. And then important is how we use it is the well performance monitoring. How is the well behaving? You're producing the well. You think you know that all your equipment in the well are functioning as it should. Are they really functioning well? Sorry, is there any questions? I hear somebody talking. Okay, it's muted now. Again, on the overburden management, how we use 4D seismic. Essentially, we analyze the overburden risks or the hazards, and we try to ensure safe operations, which is absolutely important for us in producing hydrocarbon from these particular fields. When it comes to the 4D seismic, what matters? What are the things actually matters? It's essentially two things which matters most, to keep it simple. You should have the source which you are shooting seismic repeatable, meaning two things should be repeatable. One is the position where you are shooting. So your source position should be repeatable, and the equipment in itself should be repeatable. And that's a very, very fishy thing to really repeat. Even if you try to think that you are going with the same source, with the same contractor, it still might not be repeatable, because the same source goes in through operational maintenance and it changes with time, bits and pieces, your bubble, it changes, and the source, if you feel it's same, it still changes. So it's difficult to maintain operationally, but again, that's something which is important, just to keep it a note. When it comes to the receivers, it's also important to repeat the position and the equipment. So these are the two things that we can talk about when it comes to good 4D seismic. How many different ways we can do 4D seismic? We can do it without streamer. We can do with PRMs. We can do with nodes. And also, we can do with retrievable OBCs. So when we have the ocean bottom seismometers, if we put it at one go, at one time, at another time, we think we are trying to repeat it at the same position, we can do it. So and then we acquire with the source vessel and acquire data. So there are essentially 3 to 4 ways in which we can do it, and there are different benefits, or each of the technologies, it allows us certain benefits. When it comes to the 4 component, you're quite aware that, okay, nodes, permanent seismic, and retrievable OBCs, they provide 4 component data. And streamer, of course, you're just getting the hydrophone data, so you're just getting the P component. If your shear component is important for you, then of course your choice should be one of these 3 and not streamer. And if your shear component, something in cases in your field, you feel that your shear component is not that important, at least for your reservoir, then probably it's better to go with the streamer. But there are other aspects. For example, if you're interested that the system is on 24/7, of course, you cannot do it with the streamer. Nodes is difficult to do because of the battery life, but these days nodes have improved quite a lot with charging on the nodes while it is operationally on. And retrievable OBC, since you are retrieving, it's not possible to keep it always on. But with the permanent, yes, you can. And there are specific benefits out of that as well. When it comes to the seabed coupling, it's of course good with the nodes and the permanent OBCs, because they're really, what you do with the permanent system is you put in the OBC cables ideally on the seafloor, you trench it, you put it in, and in cases where the rock surface, the seabed is very hard, you are unable to drill through that and trench it, you put the OBC cables on top on the seafloor and dump it with rocks. So essentially, they're very, very they have got a very good coupling with the seabed. When it comes to the repeatable recording locations, best to repeat it with nodes and permanent seismic. Low sea surface noise, best with these, not with streamer. When it comes to the cost aspect, of course, PRM, you in a permanent reservoir monitoring setting, the company which plans to install it, they bear the cost of it. And of course, there's an upfront cost, and that could be quite painful. When it comes to the low upfront cost, these are much, much better in terms of when you compare the costs. And that could be definitely a significant reason why we go from one technology to other, apart from the benefits that we get out of it. When it comes to the risk to the equipment failure, permanent, since you have invested your money and put it onto the seafloor, you expect it to work for 20, 25 years, there is a bigger risk because you have invested upfront and it might go bad, and then you spend a lot of money to repair it. When it comes to the on-demand, that you can get some few things, seismic surveys done on demand. The best is to do it permanent. For example, why we are talking about on demand? Normally with a permanent seismic solution, you do service every 6 months to 1 year. Roughly, that's the tentative time period. But all of a sudden, you are seeing some fishy behavior within your field due to pressure buildups, due to saturation, or there are critical wells that you are trying to drill. You might be thinking that it's very good to have an information right very, very quickly, as soon as possible, so that we are able to drill this well, or we de-risk quite a few of the things, risks that we have, and mitigate them. You plan to acquire it. You acquire as you call in your acquisition company. They come in and do it. Quick acquisition for you, and you see the subsurface picture. You make your decision. Looks very easy to do, but it might be complicated. But I'll tell a bit about it, how it has been done, and it is possible to do. And it's, of course, when it comes to the obstructed areas, it is effective to do. It is much more effective to do it permanent, and it's even more effective with nodes. Somewhere it could be much more difficult to do it permanent as well, but it's much easier to do it with nodes. When it comes to these two, it's a bit difficult to continue doing it in obstructed areas. Now, where has 4D seismic been done in a global picture? Essentially, the birthplace has been North Sea, but since 1990s, as you have seen that we have been talking about it, it has been commercially done across the world. Mainly, it has been the classic reservoirs where we have done. Later on, we have moved into carbonates, and we have done it in carbonates. We have done it in unconventionals, meaning heavy oils. We have done it in Canada, and we are seeing much more effective use of 4D seismic in unconventionals over time. And this is the distribution that we have seen in different kind of reservoirs. We have seen it, and today we are seeing more and more effective use of permanent seismic in complicated fields, much more complicated fields where we have challenges with production, or geology is way more complicated. Where we are not really sure of understanding from the perspective of geology is really, really correct. We want much more information to back it up. That's where 4D seismic is becoming much more effective. When it comes to the North Sea case, it's kind of a laboratory out over here. So I could not fit everything in the map. So the Barents Sea further north out over here, there are a few fields, Snøhvit, Collier, Johan Castberg. In this part, northern North Sea, you've got plenty of fields, mostly quite old, has been producing for quite a while. Then you have got pretty old fields out over here, Statfjord, Gullfaks, Snorra, Wiesund. Few are kind of finishing off and things like that. And plenty of all of them are ticket that they're kind of laboratories out over here that 4D seismic has been done in all of these fields. And in fields where I put in with the stars out over here, they are fields where we have done permanent monitoring. So Ekofisk is, Valhall is the first field in the Norwegian continental shelf to do permanent monitoring, and followed by Ekofisk, and then by Snorre and Grana. And then we have done it with Johan Sverdrup very recently, and Johan Castberg in the Barents Sea, it's coming next. And if you see out over here in the Norwegian continental shelf, these fields with how much life is kind of left, the volumes out over here for each of these fields, this is what has been produced. The green, light green, is essentially the residual oil which will be left after the field stops production. At least this is what we know in terms of the numbers. And this is what is left. So you see, permanent monitoring decision has been taken in when at least this much of oil is left. So think if you're Ekofisk, we took the decision of doing Ekofisk quite long back. So it has been in production, its earliest field in the Norwegian continental shelf to start production. So this is in late 2012, 14, somewhere, 2012, something like that. We started PRM in Ekofisk. We need to check the times. I've forgotten that. If it has been done much earlier, this part, which is kind of remaining in the ground, I'm sure it could have been improved and lot less potential would have been left in the ground. Nevertheless, we take it to see learning out of it. And Johan Carlsberg, Johan Sverdrup, the field which has been found recently and been put into production, very little has been produced because it has come on stream very soon. We have had a permanent reservoir monitoring in this reservoir from day one. So this is the learning that we get out of that. Gullfaks, very old field. We do not have a permanent system, probably. Very early on, if we have done it, could have been good. Snorra, it has got it lit. At least we have done it. Here in Snorra, we have done it. In Elfisk, it's not really a permanent system, but in Valhall, yes. And we have planned to do it in Kasberg, so it's going to come up. And Grana does have it. So these are some of the fields in the Norwegian continental shelf, which has got permanent monitoring and 4D seismic. So you can see it's kind of a laboratory here. Now I'll get into the topic of permanent reservoir monitoring. It was a long teaser to get you through the topic. And my focus here will be to demonstrate the digital oil field concept and how it is different from a normal 4D seismic project. So the setting out over here in a permanent reservoir monitoring perspective is that you have trenched into the seabed, or if the seabed is very hard, you have put in the OBC cables and you have rock dumped them. And then your recording equipment is staying on your platform. And then you have got a fiber optic cable through which data comes into your office and it's being accessed continuously. You've got a source vessel which goes out with a source and does the boom stuff, and you acquire the data. And via satellite, it's the source positions. When you are shooting it, it's been transferred to the offices. So all system operation, acquisition QC, processing, and interpretation, all is happening at your office. Nothing is happening in the vessel, which we are normally used to. So normally, in a 4D seismic project, we have used towed streamer. So where to the acquisition and processing, there are long-term contracts. So normally in a normal 4D seismic project, you have got one-off contracts or tendering which goes on for each of the acquisition and processing. To do all of this tendering process, it takes you 6 to 8 months of time. You spend your time and energy in doing the tendering, looking at the tenders, then you award the contract, and then the work starts, finishes. It becomes quite a long. Normally experience has been for a streamer seismic, it's 1.5 years from the start of the preparation for tendering process to getting your data on table. 1.5 years is very easily spent. But here we are talking about long-term acquisition contracts, processing contracts, so that we don't need to get on with this tendering stuff again and again. It's a say 4 years contract that we are giving, and then so that your time is being spent just on, okay, you take a decision to acquire data. Your company which does the acquisition comes in, acquires the data for you, and once you are acquiring data, it's flowing through into your office. Once you are shooting this vessel goes in and shoots along a particular line. When it is turning from one line to the second line, you are doing your acquisition QC and your processing QC. It starts everything together. So data streaming real time, your processing QC starts after the end of line shooting. So everything speeds up. And when we are talking about acquisition and processing, to give you a bit of numbers on it, when it comes to the turnaround time in processing, we have looked into when it comes to the OBC processing, ocean bottom seismic, because this is a permanent seismic project, essentially laying down your OBC cables into the seafloor. So that's the right comparison. So when it comes to the processing, we have seen it has taken up to 3 years to process for the OBC data sets. The quickest that we have seen is 8 to 9 months of processing 4D seismic with OBC cables. Here, in the first one, we have taken around 80 days to process in a 4D mode between PRM 0 and 1. The fast baseline, we call it PRM 0. The fast monitor, we call it PRM 1. So when it comes to the acquisition, it has taken 30 days to acquire. And the next one, we have taken 20 to 23 days to acquire. The processing time, first one was quite long. It was 80 days. But see how it jumps in the next one to 30 days. And then right now, this is up to PRM 4 we are seeing here. But I think we have done 11 or 12 right now, acquisitions on this since 2014. And it has come down to 7 to 10 days of processing time. So that's a significant reduction. When it comes to the acquisition, it's very important to note that what can be done here is that to make it cost effective and flexible, there are instances that where acquisition vessel has been a modified platform vessel. A platform vessel, which is usually meant for giving a platform supply vessel, which goes in and provides all of the supplies from onshore to offshore to the platform. So that is being transformed. Your back deck is being modified. You have your modular source out over here, and then you use it to tower your source at the back of it. So that's much more cost effective and it's flexible. It's very, very cheap to operate them. It's much cheaper than doing it with the normal acquisition vessels. So, and it's normally available on demand. So meaning that if you have your acquisition crew ready, it's not it's not busy with many other projects, then the vessel is easily available and you can use it. And you can have on-demand seismic. And very important to note here is that if you own a source or if the company owns a source, it's an upfront investment. But what it gives is a repeatability. And there's a shared business model out over here, meaning there could be several fields with permanent reservoir monitoring. You have spent money in doing it. And if you own a source in the same company, use it in 2 or 3 different fields, then you share the cost. And it becomes quite a good proposition that you ensure repeatability. It can be done across the company as well. That is also another business model. Dedicated crew for operations. So meaning that when you have a long-term contract and you've got the same acquisition crew, there's a knowledge continuity. And that is kind of very, very important. Fourth, and another important thing that has been done is parts acquisition, meaning that due to the weather downtime, there are many instances where we are unable to acquire the full field area. Sometimes we normally take, as you have seen here, up to 30 days to acquire. But 30 days, within 30 days, actually good weather period is say 8 or 9, not more than that. So even there are times when you might not get those 8 or 9 good days. You might be restricted to having 5 good days. What do? You are unable to shoot over the entire area. You shoot bits and pieces of it, where you think you are able to get 4D signature because of known activities within your field. You are acquiring there. There are plenty of source line which you have left untouched. How do you make it to work in terms of 4D seismic? So there has been, I put in a link out over here for a paper that has been worked on with regard to the sparse acquisition. So what has been done is that we have borrowed in traces from previous surveys in those areas where we do not expect 4D signatures. And we have combined it with the new monitor survey to as if look that that's a complete survey. And we have made 4D differences. And with 10, I think 8 or 9 acquisitions where this has been done in different degrees, I've seen it to work and work really well. But it is very important to note that you have to have a very good knowledge as to where you expect 4D signatures, and you have to repeat it there. And don't try to borrow it from previous surveys. Then let's take into the part over here. So if I get back again to the digital oil field concept out over here, there are many things that we are doing it very differently than a standard 4D seismic project. To ensure that the projects are cost effective, we are able to derive flexibility, we are able to have, we are trying to make a business model out over here which is sustainable. We are trying to have a better data quality because of repeatability. Turnaround time very short, as much so that we are able to harness the data value as quick as possible. Then the next phase is product automation. So what happens after acquisition and processing? Your processing vendor provides you the data, process seismic data. What do you do with it? You can't just start working with it immediately. Of course, you have to start working with it immediately, but you need to make certain byproducts out of it. And the key byproducts out of it, essentially, one of it is definitely you need to go for many fields go for 4D seismic inversion. There are different kind of technologies, which Dr. Shaw has covered with you earlier. There are essential 4D components with regard to time shifts and time strains. Time strain is essentially another derivative of time shift. So I've introduced with you what is the time shift. And these can be prepared very shortly. There are standard workflows now, which uses the data immediately after we get from the processing vendor. And it runs in through automated flows, through seismic inversion, time shifts, and other different horizon-related attributes, all kinds of computations. Often it can take just overnight to do all of these things. Earlier, I've done it in silos, then at least 8 to 9 years or 10 years back. And that all of these processes have taken at least a month to really do it in silos, because you have got separate algorithms sitting in different points in time and space. You have to access them. You have to access them differently. You have to write in and write out data. It's a huge, huge time wastage. And that is something that you're digitalizing everything. You're trying to bring under one umbrella so that you are having an automation in the process. And how is this automation possible? Automation is possible because you know that in this particular case, the processing took longer because we did a lot of testing. But later on, why did the processing took much lesser time? It took much lesser time because we have done the testing and we know the parameters which are going to work for 4D seismic processing. And that's what has happened. And similarly, for these particular cases, for 4D inversion, time shifts, you do the testing upfront in the first 4D. But later on, since it's a repeatable process, you're using the same source and the same receivers. And your processing flow, everything is just the same. So you're no more testing. You're just using the same parameters and just making it flow through. So then you dramatically reduce your time, and you use that time to derive value out of your data. When it comes to the non-seismic data, ideally dynamic data from the reservoir, from the production data sets, everything we have learned from our experiences. So now we are creating a platform where we have got everything which is being streamed in, your production data sets, your simulation data from your reservoir model, everything is in one place to compare it with your 4D seismic. This is upfront prepared. So this earlier, it has taken much longer time, but now everything is data preparation is a key thing, and that is being kind of kept ready very quickly after you receive your data. Okay, not much is left, but I still need to go through it. Again, now using the applications of the data set out over here. In this particular case, we are looking at a well which has got two branches, Y1 and Y2. In Y1, we have got the production screen just in here, and the black part is a blank, meaning there is no production from here. And in this particular branch, you have got production from this entire part. The places where you see is marked deep green, meaning that we have got inflow control valves out over there, which allows more oil to flow through. If it is permitting more oil, it will permit more gas as well, if you have got gas in the system. And that's how it is. If it is orange, the inflow control valves are much more stricter, so it's not allowing much more hydrocarbon to flow through. In this particular case, at this time period of 6 months in 2014 September to May 2015, you see this branch is responding, and you see that there is a big change in the gas column. This is an attribute which is called gas replacing oil, essentially an amplitude driven attribute. And you are seeing that the gas movement is quite strong out over here where you've got the screen. But what we do note out over here is this part, it is much more open in this particular branch. There's nothing happening. It's very, very silent. We expect that the gas to move in here quite strongly. We don't see it. 6 months goes off. If we look between September 2015 to May 2015, we see again this part is very silent. This part, the movement is very less because the gas has moved quite a bit close to the branch. So it has got very little space to move in. It moves in still a bit more. We see that the gas is moving quite a bit out over here and very strongly out over here in this particular branch in the next 6 months. Another 6 months on, it becomes very, very silent because there is no more space for the gas to move. It's on, particularly on the branch. So there is no 4D change happening. You see that now, you see that we have got changes out over here during this time period. Slowly it moves up out over here. There is no more space out over here for the gas to move. So it moves in the toe much more, but nothing happens here. Another 6 months passes, we see still very little happening here, and nothing happens much more because it's a gas breakout all across the well, where you have got production screens. So that's telling us something, that there is something funny out over here. I'll explain a bit in the next slide. And this is a perfect example. If we compare, this is from Grana, and this is from Valhall, where the seismic amplitude has been translated into, it has been compared with the PLTs, PLT information, the production logging tests, where the metrics from the PLTs have been plotted on these amplitude maps to demonstrate the amplitude response that we are getting as a response to the production is something that we can directly correlate with the PLTs. So this is a very, very important information that in a field-wide scale from seismic, you are getting an information which can be compared with production logging tests. So that is quite significant. In these particular cases, the movement of the gas is directly proportional to the hydrocarbon takeoff from the grana field. So that is very important. The voidage replacement out over here for the oil with the gas is directly proportional, and you can get very good metrics of production out of from these particular plots. Then to compare how is these used when it comes to the model meaning reservoir model. So if you remember Y1, EY1 and Y2, so this was Y1 and this one was Y2. We had issues in the Y2, so we tried to look back into the model and try to see what has happened. So during this time period, PRM2 and PRM1, so we are looking exclusively during this time period what has happened. Very little movement in Y1, and in Y2 it has been a movement out over here, but nothing here. Let's look at what the model is saying. The model is saying that where you have got much open valve, there should be a huge gas movement out over there. This is not something that we see from the data. We see there is a big movement out over here, which we have seen it out over there. There's a big movement out over there, which corresponds to there, and which is not in agreement with the model. So what we did, we understood that there is something going on out over here, that we have kind of either lost communication with this part of the screens, or this is not effective. There could be different reasons for it. There could be heavy sanding, screens going bad due to different reasons and things like that. So what we did on the simulation model, we applied a scheme factor. I'm not getting into the details of it. It's essentially mathematical jugglery. We have used a scheme factor out over here to mimic what PRM data is saying. This is something is significantly important in the industry. This is where you see how the collaborative approach in the data and the discipline is taking place. We are using the data to mimic the model that what the data is telling you. So we are using the scheme factor to make the model look as the seismic is showing. So this is the end result of after the application of the scheme factor. And this is the Y1 branch, which is, of course, in the earlier phase, it was looking like there's a big movement happening. But when we applied the scheme factor, then this movement reduced to this much, which is very, very little. And this is what we expected to happen. So in the initial phase, if you look at just the maps, this is what the 4D told, that there is a little happening out over here, which was not in agreement with the model. After the application of the scheme factor, this is how the model looked. So this is something that we did to the model using the data, which made the model much more predictive for future use. Another application is how do we look into the case where the instrumentation in a particular well is fine or not? How do we interrogate that? So this is one of the examples where we have shot 4D seismic after a few days of starting gas injection in this particular case. We have got packers out over here. The red areas, they are called packers. Packers are certain instruments which essentially should stop any backflow of gas injection from here, which is the green units where we are injecting. So it should stop the backflow. There could be cases in a well where you're not sure whether the packers are working or not. If it doesn't work, it's going to make the hydrocarbon to flow through this blank area up to here. In this particular case, it's a good understanding that we developed that within a few days after we start gas injection, that it is very much limited to where we are injecting, and the instrumentation is working fine. And in a map direction, when we try to look at the map, we see that, okay, this is exactly where the response is constrained, meaning the aerial influence of it. So think in terms of production logging. If it is 1D, this is a 3D. production logging, or at least in a 2D, which you can extend in a 3D sense. When it comes to out of zone injection, there has been cases where we have looked into that there's been a sudden change in some of the reflectors in a case where we have been injecting in a shallow overburden. And what we did not see this change, all of a sudden a kink in the reflector earlier. So we understood that there is something funny going on. And this is one thing that from the point of when we have observed this on 4D seismic or PRM datasets, we have taken 1 week to stop this particular well from injecting any more into the overburden in order to avoid out of zone injection. So this is data-driven decision making. It has taken probably tons of meetings, 10 to 12 meetings, to make that decision that we are going to stop it. This well has been injecting for a significant amount of time. Probably this well has been the longest injecting well in the Norwegian continental shelf. And that was a decision was taken in a week of time. Then when it comes to the passive or microseismic monitoring, there are cases where what do we do with microseismic monitoring or passive seismic? Essentially, we keep listening. We are not doing any active seismic, meaning we are not going out with a source to shoot. We are continuously listening to these monitors, to all of these receivers, which is on the seabed, and we are detecting on the recorders, and we are continuously analyzing the data. So this is something that Equinor has worked on to develop a project which is called Sentry. Essentially, the motivation of the project has been, we call it monitoring the sound of silence. And we have been trying to listen to this sound and trying to understand what is happening in the reservoir or in the overburden when it comes to west injection, for example. Is it fracking up somewhere? It is going, or you're doing a hydraulic fracturing somewhere. Is it doing something funny? It's going out somewhere. We need a mechanism to understand if something is happening. And to get an alarm system out of this message, do your data analytics, screen out the signature out of the noise, put an alarm system and aware the people that all of these things are, few things are going on in your reservoir or button, which you need to have a look on. And that's where when you get an alarm as an email, we just dive into the data set and look into the specific area if something is going on. So that is something which is kind of significantly important, which permanent reservoir monitoring gives us. Then another thing is distributed acoustic sensing, meaning in your well, you can put in a fiber. This fiber allows you to have a continuous record of information. Different things. It can be, you can use it for your microseismic monitoring along the well path. You can use it for your VSPs. You can use it to interrogate your completions. You can use it for your flow monitoring. There are different aspects in which you can use it. So this is kind of a part in which you can think disruptive technologies are being put into use in an in-well concept. And going through all of these things, all of these examples, now it's probably time to summarize and go into the Q&A section. So in order to summarize what we have gone through, or what I've tried to essentially cover, is to demonstrate the end-to-end process automation. It's not that we have been able to do it, but the objective is to go into the mode of end-to-end process automation. Second, develop a collaborative culture. Whether it comes with the acquisition vendor or the processing vendor, to the company which gives the project, to the other disciplines whose data is equally important or needs to be looked at together with seismic. We need to be very multidisciplinary out over here and collaborate in data and as people. We need to reduce the turnaround time to harness the value. And why is it important? The reason out over here why the turnaround time is very important is that the value of 4D seismic in reservoir management, it falls with time. The fresher the data, the value is more. So you can impact your field decisions much more when the data is fresh. If you take much longer time from the time when you have acquired the data to start, if you have taken 1.5 years of time, majority of your value is gone and you are probably working somewhere there. If you have got your data in 15 days or 20 days of time, you start harnessing your data value right from here. So that's the difference. And then multi-technology approach is absolutely important because that's where you try to aim to know more of the unknowns. There are a few things that we think that we know, and that's what I'm talking about. Our many industry professionals are going to talk to you about things that they know, but there are plenty of things that do not know. And that's where technology comes into the picture to harness the value. And that's why we are trying to use technology to increase our understanding. Another important thing, as I've highlighted, improve data quality to enable better decisions. I've shown a couple of examples on it, why. And of course, is on top of it is data-driven decisions. That is significantly important. I've tried to lay stress on it at different point in time. What are the data-driven decisions? That ends my talk. Now the floor is open for questions.